Fourier's law of heat conduction showed us how much energy per unit time flowed through a particular linear surface, one-dimensional. Now you could look at 2 or 3 dimensions, but 1 dimension actually is usually sufficient because there'll be a heat flow usually in just one direction, though some problems require a more complicated look. I'm going to stick with 1 dimension, but what if we had a cylinder instead? Well, our dx would become a dr, and the area would be 2 pi rl, the surface area of a cylinder. Let's use separation of variables, and we'll solve this. The difference here is we get a 1 over r dr, getting the natural log of r2 minus r1. After rearranging this, I end up with my expression for the heat transfer rate via conduction for a cylindrical shape with an inner radius r1 and inner temperature T1 and outer radius r2 and temperature T2. As before, we could think of a particular thickness of cylinder as acting as a thermal resistor. And then you could combine different ideas, like maybe including the convection on the outside. This was the way I might think of, insulating a hot water pipe or something like that. It is a little interesting as you look at the geometry, however. As you increase the amount of insulation, you are reducing the conductivity, but you would be increasing the convection on the outside. For most practical purposes, if you want to insulate a pipe, for instance, it's still better just to add more insulation. But depending on the materials and actually for insulation itself, for the first little bit, actually, as you add more insulation, it would be a better thermal conductor. More heat would transfer out because sort of the convection component is winning. You could go through and work out the same kind of ideas of both Q dot and kind of thinking through the different components of conduction and convection for a sphere as well. This would basically just change your area back in our Q dot equation, so you'd reintegrate, get a different formula, and then you could also work out another thermal resistance or resistivity for a conductor of a sphere with a particular radius, inner and outer radius. Using the idea of a resistivity network, then you could combine, say, even different layers. I guess I just had an egg for breakfast, so I was kind of thinking of, you could think of the different shells, each with its own conductivity, and you could figure out the overall thermal resistance.